Hello and welcome. In this workshop, we will demonstrate how to use the Ansys Fluent meshing watertight geometry workflow to generate a simulation-ready mesh that can be used to study the fluid flow through a stop valve. We will start with demonstrating how to import a body of influence geometry and add a BOI local sizing control to refine the mesh at the valve section to capture the complex flow dynamics during the simulation. We will also see how to extract fluid regions by capping the openings of the solid geometry. Finally, we will look at how to create boundary layers not only in the fluid region but also in the solid regions. Let's get started. Launch Ansys Fluent in meshing mode. For this demonstration, double precision is enabled and 4 processes are engaged for meshing. Once Fluent meshing launches, select Watertight Geometry Workflow. In the Import Geometry task, leave all the settings to default and load the provided geometry file. The geometry consists of only one region, that is, the solid domain of the stop valve. This solid domain will be used as a reference to extract the fluid domain later in the workflow. It is important to note that we need a refined mesh at the valve section to facilitate the accurate capture of the complex flow dynamics during simulation. For that, we will be using BOI local sizing control. But before that, the imported CAD does not have the BOI geometry. So, we will import the already created BOI geometry separately with the help of an additional task in the workflow. Right-click on the Import Geometry task. From the Insert Next task, select Import Body of Influence Geometry. A new task appears in the workflow. Here, load the provided BOI geometry. Note that it is only possible to import BOI geometry before the Add Local Sizing task. In the Add Local Sizing task, select Yes to add local sizing. Select Body of Influence as control type and enter 1 mm for the target mesh size. Select the BOI geometry from the list of labels to apply the control and press Add Local Sizing. As soon as you press the button, the BOI disappears from the displayed geometry. This is because Fluent meshing recognized that the body is not a part of the geometry but just an entity that drives the local mesh refinement. Next, in the Generate the Surface Mesh task, set the minimum mesh size to 1 mm and maximum size to 3 mm. Note that the imported geometry does not have labels or named selections defined at the CAD level, and hence it is considered as a single entity, as can be seen here. Therefore, we will have to separate the zones based on angles while generating the surface mesh. This is necessary for extracting the fluid domain, as the capped surfaces are created in reference to the adjacent solid zones, which of course needs to be separate entity. Therefore, set this option to Yes and keep the separation angle to its default value. Execute the task to generate the surface mesh. Once the mesh is generated, look how the zones are now defined independently. In the Describe Geometry task, under the Geometry type, select the geometry consists of only solid regions. As we have to cap the openings and extract the fluid domain, set this option to Yes. Now, set the next inputs to No and move to the next task, that is, Enclose Fluid Regions task, which is used for creating the caps for the fluid domain. To create a cap, the surface mesh that surrounds the opening needs to be selected. At the inlet pipe of the valve, select this zone using the graphic window, set the zone type to velocity inlet and click on Create Cap. Similarly, create a cap at the outlet pipe with the zone type set as pressure outlet. The names for these caps are auto-populated based on the zone type selected. In the next task, that is, Create Regions, execute the task without any changes and notice how the fluid region has been extracted. In the Update Regions task, make sure that the fluid and the solid domain of the stop valve are assigned with fluid and solid region type respectively. Next, in the Add Boundary Layers task, add 3 layers on the walls of the fluid region and 1 layer in the solid region, keeping rest of the inputs to their default settings. Adding boundary layer in the solid region will help to accurately predict the temperature gradients while performing the CFD analysis. Finally, we will move to the Generate the Volume Mesh task. In this workshop, we will use the Polyhedra Fill With method, which is the default, to generate a conformal polymesh. Leave all the inputs to their default settings. Make sure that the Mesh Solid Regions option is ticked before executing the task. Hit the Generate the Volume Mesh button to create the volume mesh. The generated mesh has a total of approximately 0.12 million cells with a mesh quality of 0.2. Hence, we have generated a good quality conformal polymesh as can be seen from this sectional image. That brings us to the end of this workshop.